Hello students. My name is Shayan Mitra, faculty member of Department of Electronics and Communication Engineering of Greater Kolkata College of Engineering and Management. Today's topic is about the LSI system, or that has been known as linear shift invariant system, or it could be said as a linear time invariant system. So for this is the module 2 that I am going to discuss, and this in this next upcoming 6 lectures I am going to give you the whole understanding of linear shift invariant system, or it could be said as linear time invariant system, and the causality of a system, how the convolution works, how the any digital system has response to a step input or impulse input, and the different kind of basic structure of LTI system, and how we mathematically represent a LTI system using difference equation. Okay, so let's begin with the lecture. And the subject name is, as you have already know, the subject name is signal system, and code is EC303, and this is the lecture number 7. Okay, so as we have discussed earlier that we are going to discuss about the LTI system. So let's begin with it. Now first of all, as we are saying that I have been taking all my references from a very popular book named Oppenheim and as a Willy India publication. Of the book has been written by V. Oppenheim, and through this, using this book, I am going to describe how all the impulse response, step response of an LTI system works. So first, we are going to express or understand all the mathematical representation using different kind of mathematical examples, and how the impulse response work. We'll discuss this in this along the way. So first of all, we have to first realize that what is an LTI system means. LTI system means it's a linear time invariant system, and in this case it is also been a causal system. So as we have in this earlier lectures, we have also described that what is a causality means. A causality means a signal which, suppose if I have to mention a signal which is causal, it means that a signal will be present, a signal will have a real time value, basically an integer value or a real time value, if the input is greater than 0, and if the input value is less than 0, then there will be no signal exist. So this will also be applicable for a digital system, where if we have to consider a system, a digital system, if we have to consider digital system causal, it means the input signal. Suppose if we have an example of this, we are going to go through these examples. Now suppose, before expressing how, suppose this xn is an input signal. Now suppose the value of n is less than 0, then there will be no output for this digital system, and if the value of n is greater than 0, and if there is a output exists, then it would be said as a causal system. And if we are talking about a linear time invariant system, that we have already discussed what is a linear time invariant means, and when you have to mention a time invariance, it means a signal, if maintain its invariant form, it means with variant of time. Suppose, as you have said, that LTI or LCI, if we are saying the linear shift invariant, it means invariant means it will not change. It means any kind of LSI or LTI system will consider as a waveform preservative system. Or suppose a digital system, it is known as LTI or LSI system, it would be considered as a waveform preservative. Simple way, it could be said in this simple way, that it would be known as linear invariant means it will be waveform preserver. It will preserve the waveform. How it will works that way? Suppose there is a input. Now if we have to take an example here, we have different kind of examples here, but first I am going to describe it in verbally, then I am going to give you different kind of examples. Now suppose a signal has been fed to a system known as xn, x of n, and we got a simple output y of n. Now that x of n has a specific pattern, a signal pattern, and the output of that specific signal will also have a specific pattern. Now suppose we delayed the signal. Suppose we utilize x of n minus 1 or we utilize x of n plus 1. We advanced or delayed the signal. Now at the output, the output of that specific signal will also be delayed or advanced as according to the input fed by the system, but the signal form, the waveform or the signal structure will not going to pollute it. It will be preserved, it will be same as it is before the delayed or advanced signal has happened. So this is basically known as time invariant. And if we are talking about linearity, what does the linearity means? Linearity means that suppose we have an input signal which is 0, the output of that signal will be 0, and suppose we have multiplied the input signal with some coefficient or some constant, the output of that signal will also be multiplied by that same constant with same magnitude. So if we have I have already discussed all these things, but because we have to understand why the impulse and step response is important for LTI system, and only if we use a linear time invariant causal system, we can imply the impulse response and step response. We can use that impulse response or step response in a system. Without a linear time invariant causal system, that impulse input or step input within a system will not be as applicable as other systems. So it is very important to understand why a linear time invariant causal system is required an impulse or step response, why the impulse and step response is important to include in a LTI system. Now as we have now discussed what is LTI and C means now, or LSI, it could be LTI or LSI, both are basically is referred to the same meaning or same characteristics of a system. One is known as linear shift invariance, another is known as linear time invariance. So as you already now have discussed all these three basic characteristics of our LTI system, causal system. Now we are getting to the real structure where we discuss about the impulse response and how it works. Now first of all, now if we have to show that how it works, suppose now first before getting into the impulse response, we are going to give you a simple example how a simple signal can be described as a impulse response. Now and then we will go get into the convolution sum. Now suppose we have visualized a signal. Suppose this signal this is the signal. Okay, so first we have taken into consideration of a signal is this x of n, where -4 there is a value, -3 there is a value. This is the basic input signal that I am going to feed into a digital system, which is a linear time invariant causal system. Now if you take a close look here, that it could be understandable that this specific signal can be understandable using an impulse responses. How it will work, let's see it. Now suppose this is xn. Okay, so this is the signal form. Okay, at -4 it has some value, in -3 it has some value, -2 it has some value, -1 0 1 2 3 4. So all in the, it's a specifically a discrete time signal where we have quantized the independent variable time, which is independent variable, which is time. We discretize that independent variable and we have given it a name, the integer value. We have given it a name of integer value, and each integer value, it has a specific amount of amplitude. So we didn't quantize the amplitude, so that's why it is not a digital system, it is absolutely a discrete time system. A discrete time system can be written as a continuous time system, but it is not specifically not a digital system. A digital system, a digital signal and a digital signal can only be realized by quantize the amplitude of that specific integer value. Now suppose we have value at -4, we have value at -3. Now we have to quantize all those amplitudes, then we will get a discrete a digital signal. But at this moment this is a continuous time signal and also a discrete time signal. Okay, so now this signal can be written as x of minus 2 del of n minus 2. Why? Now if we go to the first mathematical operation, now take a close look at here, that this is x of minus 1 del of n plus 1. Now what will happen? Now suppose I put n is equal to minus 1. Now when we put n is equal to minus 1, what will happen? This x of minus 1 into del of n plus 1 will provide you the amplitude, and the same thing will happen in case of n is equal to 0, in case of n is equal to 1. Why? Because when we put n is equal to minus 1, that impulse response will provide us a del of 0. Then only the del of, and we already know that a impulse signal only provide you a magnitude when n is equal to 0. Now that way, to configure or to achieve that specific significance in a signal, what we have to do, we have to make this part 0. So make this part 0, what we have done, we have provided it with a n plus 1. Now as soon as we take a n is equal to minus 1, that this whole function will convert into del of 0 and it will provide you a value 1. So with that one value and with this value, this is x of minus 1. So this x of minus 1 can only be realized when we provide you a impulse signal of del of n plus 1. So if we multiply the del of n plus 1 into x of minus 1 at n is equal to minus 1 only, and only if that n is equal to minus 1, this value will be realized. It means the value, the amplitude of x of minus 1, suppose this is the x of minus 1 and this is the value of the x of minus 1, so we'll get that value. Okay, and the same thing will happen in case of n. If you put n is equal to 0, this is also 0 and this is x of 0, so x of 0 is multiplied with del of 0, and which is 1, so we will get the direct value of x of 0. And the same thing will happen here, x of 1, and only if we take the value n is equal to 1, we get a del of 0 and we get x of 1 into del of 0, which is 1. Then we will realize the value or the magnitude of x of 1. So this way, what we can do, we can provide you a series of combination of signals which can provide you the x of n. Okay, now, and also that one thing you have to know, that as we have already seen, that suppose this is the signal. Okay, this is the signal where it is in between from minus 4 to 4. This is the signal. This signal can be written as in this way. Suppose x of minus 2 into del of n plus 2. Okay, so n is equal to minus 2. If we put n is equal to minus 2, what we will get? We will get del of 0. Del of 0 is 1. Then we can easily realize the value or the amplitude of x of minus 2. The x of minus 2 is this. The same way, we can realize the value of x of minus 1, this one. This is the minus 2, this is the minus 1. Okay, so this has been written here. Same way, we can also realize the value of x of 0. With the same way, you also can realize the x of value of x of 1. Okay, this way, up to this we can realize this. Now suppose this example is provided with the condition that the value of n should be in between minus 2 to plus 2. But you can, as we are discussing the problem, that's why you have taken that condition. But there could be a problem where there is a condition where we can provide it with a minus 4. The condition we could be provided with that the value of n should be in between minus 4 to plus 4. So for that reason, we can construct that this whole signal using 1, 2, 3, 4, 5, 6, 7, 8, 9 different signals. Each signal, suppose this signal can be written as x of minus 4 into del of n minus 4. Sorry, del of n plus 4. This signal can be written as x of minus 3 into del of n plus 3. Now, as soon as we put the value n is equal to minus 3, this signal will be x of minus 3. This signal will be x of minus 4, and the same way this signal will be x of minus 2. This signal will be x of minus 1. This signal will be x of 0, and this signal will be x of 1. And the same way, we can understand. We can understand all the whole signal. It means that a specific signal which has a condition, it could have a condition. It's a finite signal. which is in between -4 to +4, can be rewritten as the combination of 8 or 9 different signal, as if we add all these signals, x of -2 into del of n plus 2, or x of -4 into del of n plus 4, x of -3 into del of n plus 3, same way 1 2 3 4 5 6 7 8 9 9 signals. If we add these 9 specific signals, we will get this signal. So what we have understand from this example is that one signal, that is what has been written here. Okay, that x of -3 is del of n plus 3, this. So the whole signal, the x of n, this, any kind of a signal, any kind of a discrete time signal, which is also continuous time signal, can be written as a form, written in a form where we use the impulse signal. We multiplied x of -3 with the impulse signal, and this way we have taken 8 different signals. We add those signals and we get the original signal. So one signal can be written, can be written in this form. Okay, so this is the x of n, and it could be written as this one. Now as we have, now here what you have yes, here we have realized that the condition for the example in this book, the condition has been taken here that the value of n in between should be in between -2 to +2. That's why we have taken 1 2 3 4 5 different signals. Now if we add these 5 signals, we will get the structure where we get this part of the signal will be included. These two signals are being excluded for the mathematical purpose of this specific book. Okay, you can, if it is required, you can explain or you can realize any signal using impulse signals. Just by adding all those signals, you can realize the whole signal. Suppose instead of using this signal in exam or in any different example, we can use a signal where we have 10 or 12 or 15 samples, 20 samples, 50 samples, any number of samples you can take, and you can achieve that signal. You can achieve that signal just by adding the signals in this way. Suppose there is a signal in between n from -10 to +10. The same way, the same process will be followed to achieve this specific signal. Okay, just by adding x of -10 into del of n plus 10, x of -9 into del of n plus 9. This way you will reach x of 0 into del of n, and then you will start again x of 1 into del of n minus 1, x of 2 into del of n minus 2, x of 3 into del of n minus 3. This way you can achieve that 21 sample signal, which is in between -10 to 10. So it is a generalized format where we can achieve, we can form a x of n signal, x of function n signal, any signal. Any signal means a discrete time signal. We are talking about only discrete time signal, where we can use the impulse signal to form any kind of signal. So it means that any discrete time signal can be represented using a impulse signal. Okay, so this formation, the whole format can be written as this way. Okay, x of n is equal to summation of x of k into del of n minus k, where value of k will be between -infinity to +infinity. Now if we are talking, now this is a generalized form, absolutely a generalized form. Now if we are talking about a causal signal, what we will do, we will just discard the range where the range of -infinity. We will consider the value of k from 0 to infinity. Okay, so this is the realization. This way we can realize any kind of a discrete time signal. Now if we are talking about a causal signal, what we will do, we will just discard this -infinity. We will take k is equal to 0 to +infinity. Okay, and now this format of signal can be rewritten and can be fed to a digital signal, which is a linear time invariant signal. Because in case of a linear time invariant signal, first of all, the linearity and the additivity property will help us to realize this signal. Suppose we have used a digital signal and we have fed this signal in this way. we have used a impulse response signal, okay, and we have fed that, okay. So as we have fed it, we will get the same specific digital signal at the output, okay. Now if that signal is not linear or time invariant, it will not give us the desired output. In case of linear, as we know that linearity always considered or always follow the homogeneity and additivity property, in case of additivity property. So if we multiply this value, the output will also provide you a desired output of this specific value that has been multiplied with x of minus 3. So the additivity property and the multiplication property, which is also a homogeneity property, should be considered when we are dealing with a signal which has been written in a form where we have used the impulse signals. So only and only if the LTI linear time invariant causal system can only deal with this kind of a signal where we have considered the impulse signals, okay. So now we have understood what is the linear time invariant causal system and why we have used the impulse responses. The impulse response is also important. We have also already discussed that a signal, a discrete time signal, can be written as a in a form of additive form, and the generalized form of that of any discrete time signal can be written as this. This is a very important. Sorry, this is okay. One second. Yes. This is the format. Okay, this is the real thing. We have just written the whole format in a generalized form, okay. Just what you have to do, we just have to add the values. We put k is equal to 0, we put k is equal to, we have to put k is equal to 1, we can put k is equal to 1, 2, 3, 4. And now you can also deal with a non-causal system or non-causal signal using, or you can express a non-causal signal using this specific expression, okay. So let's get on with. So we have realized that what is the impulse signal is, why it has been used in a LTI system, and why it is required to have a digital signal which is LTI, it means linear shifted invariance or linear time invariant, to deal with impulse signals, okay. So okay, so now suppose now the same thing, the same way we can also write. Now we have already know that what is step signal is. A step signal is a signal which will be 1 when the value of k will get than equal to 0. When it is less than equal to 0, it will not be considered. So the same way we can write this. Simple. We can write a value. Okay. Put 0 in place of k. We'll get n. Now value of n at 0 will be provided when you put 0. Okay. Now if we put del of n, we put n is equal to 1. It will be not 1, it will be 0. So when k is equal to 1, the 1 and 1 will cut out, and we will get del of 0. So one generalized form that we have already written, we have already realized that how we have described that summation of k is minus infinity to plus infinity, we can write x of k into del of n minus k. The same way we can write also step signal in this format. The same process will be followed. The same process. Okay, just we have to change the value of n. Simple. We just have to change the value, and we have already know that it will always be expressed that what is the value of n will be. Suppose we will take the value of n in between minus 2 to plus 2 or minus 4 to plus 2. That specific range will be given. Okay. And another thing that we need to understand, that the whole equation, the equation that I have already realized, is also known as shifting property. Okay. Of discrete time unit impulse, and always like impulse is a unit impulse signal. Okay, so because the sequence del of n minus k is a non-zero only when k is equal, that's also important part, that when this only non-zero only when k is equal to 1. Simple, that we have already realized that if the value it only and only if it will realize it will be a non-zero value only when that n equal to k. Suppose n is equal to 1 and k is equal to 0. What we will get? We get del of 1. So del of 1 will not provide you any amplitude, right? It will not provide you any amplitude. So a step response can be defined with the impulse response, and the specific signal can also be realized using the impulse signals. So that is the most important characteristic that we are going to discuss in the next lecture. So up to this we have realized what is an LTI causal system is, and why we can use any kind of discrete time signal using the impulse signals. A specific discrete time signal can be realized as the summation of different impulse signals. So using impulse signals we can realize a specific discrete time signal. So up to this we will end this lecture here, and we have already discussed what is shifting properties. In case of shifting property, we know when k is equal to n, we will get a non-zero value. The summation on the right hand side equation to shift through the sequence of values. So that's what is known as shifting property. We have to shift through the sequence of values x of k and preserves only the value corresponding to k of n. We'll okay. The same thing is realized here, that when k is equal to 1, we will get a value of del of n minus k, and we have to shift through all the value of n, and only when we will get a specific value. So we'll end our discussion here. In the next lecture we are going to discuss how we how the convolution works. We will understand what is the convolution, and in the next lecture we are going to discuss convolution. Okay, thank you. Okay, bye.